Morning, folks. Hopefully, you're having a good day by the time we're watching this. I did I did promise to do a video explaining the model which I've developed using Haversine Formula, which is traditionally used in geophysics, basically to calculate ge- geodesic distance on a curved surface. Basically, that is meaning that you're calculating the shortest path on a curved surface, and how I have adopted it to utilization within the financial markets. So I think this this is the screenshot that I shared of the mathematical representation of the model. So I'll get into the integrates of the various components of the model and what is really going on, and hopefully this video will be helpful to bridge the gap whereby you might have failed to understand. So the first thing that I do, even if I'll also share samples of the code base, is calculate the GAC, the GAC model for volatility estimation of the energy prices, of the changes in the energy prices. So GAC is the generalized autoregressive conditional heteroscedasticity. If you are familiar with time series analysis, then you know that heteroscedasticity refers to changes in variance. So basically, that is what you are doing here. So you're calculating um, the volatility of energy price changes. Um, in this instance, I'm using natural gas, electricity, and oil. And then also, the GAC model is specifically of interest because it captures the stochastic properties of these drivers. So that is natural gas, electricity, and oil. Then I utilized the trended fluctuation analysis and multifactorial trended fluctuation analysis, so that is DFA and MFDFA, to be able to select my lag values. So this one's what they basically do is basically capture the fractal properties of our time series. Perhaps what I've forgotten to put on here is the calculation of the Hurst exponent, but it is in my code. Let me just show you. Yeah. So this one. So calculation of the Hurst exponent. So the Hurst exponent is basically the statistical measure that quantifies the long-term memory or persistence of a time series. It indicates whether the time series follows a trend or it tends to revert to its mean. So if normally it ranges between 0 and 1, so that's why I'm utilizing basically the absolute value. If the value of the Hurst exponent is 0.5, then the time series is purely random. That is, it has no long-term memory. If the Hurst exponent is greater than 0.5, then it suggests that the time series is persistent or that it has a trending time series, and that the past values have an influence on the future values. Then if the Hurst exponent is less than 0.5, then it indicates anti-persistence or that the time series has a mean reverting nature, where the past values tend to revert to the long-term mean. So you will note this is actually true uh, for energy prices. Energy prices tend to have a Hurst exponent which is less than 0.5. I will share that later on. So then once I do that, I carry out normalization. This is basically to set the values of the targeted inflation and the changes between 0 and 1, basically to set it up for the utilization in the Haversine formula, because you note that it utilizes a sine and basically it's just trigonometry. So the values need to be between 0 and 1. And then we have our A term here. Uh, okay, let me just show you the Haversine formula and how it looks like. Okay, where is it? There you go. So normally the Haversine formula looks like this. So here we have A which is normally on the usual basis is calculated as sine squared times the change in latitude over 2 plus the cosine of lat 1, latitude 1, times the cosine of latitude 2 multiplied by the sine squared of the change in longitude. Basically, you're normally given the longitude and latitude values. Then we calculate C, which is 2 times the arc tan 2 times square root of A times 1 minus the square root of A. So the square root of 1 minus A. And then the final distance, now they have a sign distance, is given by dr times C, which is this. So r, which is the radius of the earth, is given by 6371. This one is a constant. So then here we are getting our A value by calculating the weighted sum of the normalized economic variables. So we have already normalized our economic variables, that is the change in energy prices, that's the change in oil, change in electric prices, and change in natural gas. And then also we have normalized the change in inflation. So from the targeted inflation to the maximum value of the inflation, we have normalized all of those variables. So A is basically the weighted sum of normalized variables. And then once we've done that, we come and calculate now the Haversine distance. Uh, the Haversine distance is basically 2 times r in this instance, which is 50 times max of the Haversine exponent of the absolute Haversine exponent of natural gas, electric prices, and oil. So this one becomes 2 times r, arcsine of clip. Again, we are constraining the value of A to be between 0 and 1, then times the inflation minus the target inflation over the maximum inflation minus the targeted inflation times the power. In this instance, I was utilizing 1.2 and 2.0. This is after basically experimenting. Okay, so I've been asked a question, a really interesting one, as to why I'm only considering like the Haversine distance and not the Euclidean distance. And my reasoning is quite simple. I'm coming from an nonlinear perspective. So, in order to best capture these nonlinear properties, I'm using the Haversine distance rather than the Euclidean distance. So, fractal properties of economic time series as identified by Mandelbrot. If you have read his work in 1982, suggests that the market exhibit self-similar scale invariant patterns that may not align with a flat plane. So Euclidean distance normally is the distance between is a straight line. Basically, it's a straight line, and it assumes that distance occurs on a flat plane. But the geodesic distance um, is the shortest path on a curved surface. So on a flat plane, but rather multidimensional curved manifold. So I'm assuming that conceptually, the financial markets in this instance is a curved surface, and that's why I'm using it to capture the nonlinear properties of the time series. So yeah. So basically, what I'm using this formula for is to where is, so I'm writing a paper on is to determine how far can energy prices be pushed before they have let's say catastrophic a large effect on inflation, a negative effect on inflation. But keeping up with economic literature, we see that over time the effect of energy prices on inflation has reduced, but regardless, they still do have an impact on the value of inflation, because kila mse anajua basically whenever energy prices tend to rise, um, we tend to expect that the prices of our day-to-day commodities will rise as well. So our food prices, our the value of our electricity will also go up. Um, yeah, basically, like, cause transportation, uh, which requires energy input from these various commodities that you're using, tend to tend to influence the eventual prices of the commodities. It's passed and it is passed on to the consumer. So even though the effect of energy prices on inflation has reduced over time, still it has some impact. It's there. It's there in our mind. We literally see it. So this is the paper that I'm writing. So it is anticipating inflation, tipping points in energy-driven economies, and for my data set, mostly I'm using Germany because Germany tends normally to be impacted. Them generally no, normally tends to follow this assumption, right? So let me show you the code base and how it's functioning. So like I've said, even for the importation, it's just basically common statistical values, not really much there. Then I wind up calculating the Hurst exponent, as I've already explained that. Then we wind up doing fractional differencing. So when I'm carrying out fractional differencing is that, okay, so for those who are familiar with time series analysis, fractional differencing basically is to take care of the components of the time series. So things like the trend, the seasonal effects, and the cyclical effects, you want to eliminate them from the time series. But then fractional differencing does this, but also maintains the long-term memory of the time series. So that's what fractional differencing here does. Then I've already explained the purpose of DFA and MFDFA, which I'm using to calculate to select my lag values. So that is my importation of the data. Now the calculation of the Hurst exponent, like I was saying, energy prices tend to have a Hurst exponent that is less than zero point 0.5. So you'll see actually this is true if we are to check on energy prices. Just a minute. If we are to check on energy prices, so we take something like natural gas, which is one. You'll see that in the long run, uh, natural gas natural gas tends to oscillate around given certain price points. Now let's go to the 1 week. Yeah, like you'll notice like there is oscillation within certain price points. It doesn't exceed certain price points. Just oscillates within there. See, the highest price has been 10 in the 10 and as fast 2015, right? If you check on oil, you'll find that it is the same case. Prices tend to oscillate within given price points. So, like you can see, the highest price at AJ exceed 80. This is the US oil. Exceed. It is this. I'm exceed 80. Some point. Okay, sorry. So you'll see that it tends to oscillate within certain price points. So it tends to revert towards the mean. So as far as I can remember, most energy prices was in a range between 70 and 50. I haven't experienced easy price points za huku chini yet since I started trading in this one. Same case for, yeah, on this other end as well, right? They tend to oscillate within given price points. So it's less than zero point 0.5. That is in the long run, right? So that is that. Then we calculate the GAC. Uh, as I've explained initially, this is just used to calculate the volatility in the price changes and also capture the stochastic properties of the different energy drivers. So natural gas and oil and electricity prices. So then we have the tipping points. For the monthly, I defined it as 0.35, and for the annually is 4%. So this one is normally in line with central bank policy all over the world. Most of them they want to keep their inflation rates between 2% and 4%. If it starts to exceed beyond that, then you see the central banks taking measures in order to reduce the inflation levels back to 2%, basically within that range, so that it doesn't negatively impact the economy. This is just a lag selection. You can see what our MFDFA does for selection of our lag values. Then we apply them. Yes, so I also incorporated the volatility lags and lag for inflation values, and this is our value for R. Right, I normalize the time series as I've explained already, and then now this is our Haversine formula and what it is doing. This is, it looks lengthy, but it is basically just this value for A, and then we wind up calculating the Haversine distance right there. Okay, so then we proceed. Calculating the Haversine distance. This is just a summary of the lagged values, and then the Haversine distance summary. And okay, so I use the basically just to penalize larger values. I use a consist sensitive F1 score. Now then I use grid search to determine the most optimal threshold for the Haversine distance, right? And I use a phone score together with the grid search to be able to select this. The other methods you could consider looking at Poel's method for getting your threshold values. It could possibly work. I haven't tried it out. Um, yeah, and there's this. So I've determined the optimal threshold value for using grid search and the optimal threshold value for the annualized same case. Then once I'm done with that, I now evaluate my model. You can see for the annualized, the performance metrics are really well balanced. So 0.97 for accuracy, 0.94 precision, and recall is 0.73. But for the monthly, sort of not yet there. That's why I was considering adding the Lyapunov exponent. So this is my eighth variant. I am not yet done implementing it. Um, but we'll see how it performs once I incorporate the Lyapunov exponent into it. So I'm guessing that is it. If there are any questions, feel free to reach out. I'll try and answer them the best way I can. So this is just the plot of the tipping points. You can see how it was marked out. So those are for the annual. These ones are for the monthly. Yeah, the monthly isn't really that accurate. So I'm guessing that is it. I don't think there's anything else. So hope you folks have a good day. Um, yeah, talk to you more.